Thanks for watching this video. The topic of this paper is solving portfolio optimization problems with particle filter. This presentation consists of problem formulation, particle filter, PF-based optimization scheme, simulation results, and a brief conclusion. Portfolio is a combination of security investment. The goal of portfolio optimization is to obtain returns and reduce risk. Higher market risk mean variance model is the most commonly used model to minimize investment risk under a certain expected return. The mean variance model is nonlinear optimization problem with multiple conditions. Heuristic algorithms are popularly used to solve nonlinear optimization problems. Genetic algorithm, particle swarm optimization, and simulated analysis have been widely applied in solving portfolio optimization problems. However, some defects will decrease the precision of the optimization, such as point to track into local extreme points, coverage geometry, and deep rely on parameter settings. Thus, we do not consider utilizing this method to solve portfolio optimization problem. Here is the mean variance model. The objective function of the portfolio optimization problem is presented in equation 1 and is subject to equation 2. The goal of the mean variance model is to minimize investment risk under a certain expected return. Here, N is number of security. Omega I is the investment rate of the security I. Mu I is the expected rate of the return of the security I. Sigma ij is covariance of the expected return between the security I and the security j. In this paper, particle filter method is considered to be utilized to solve the portfolio optimization problem. Particle filter is used to solve filtering problem of nonlinear and non-Guoxing systems. Schematic of particle filter method is presented in Figure 1. As shown in Figure 1, particles are sampled from solution domain of the object function. Probability density of the state can be approximated by a law of particles and their weight. Therefore, the state of the system in the moment k can be estimated. Update function of the state is given in equation 3, and the measurement function of the system is given in equation 4. Then, according to particle filter method, the estimated state is defined as a weighted sum of the particles, which is presented in equation 5. the update function is nonlinear, so is the measurement function. The state of the system can be estimated according to samples and their weight. Particle filter method is designed for solving filtering problem instead of solving optimization problem. To solve an optimization problem, conversion from an optimization problem to a filtering problem is needed. Then, particle filter method can be used to solve optimization problems. Assume an optimization problem is iteratively solved. Then the process of the optimization can be considered as a nonlinear dynamic time-balancing system. The number of the iterations is regarded as decreased time of the system. The optimal solution of the objective function is regarded as the state of the system. Then, change of the optimal solution during the iteration is regarded as the update function of the state. The objective function of the optimization problem is regarded as the measurement function of the state. Eventually, an optimization problem is converted into a filtering problem. So, particle filter method can be used to solve the portfolio optimization problem. Schematic of the proposed optimization scheme is presented in Figure 2. As we can see, is an iterative optimization process. The state of the system is initial when is iterative update. When the iteration is over, the minimal valence estimate of the system state is obtained. In other words, a global optimal solution of the objective function can be obtained. Details of the proposed optimization scheme are as follows. Step 1. Initialization. The state is initialized as a random sample of the solution domain of the measurement function. Step 2. Iteration. The state will be iteratively updated and converge on the global optimal solution when the iteration is accomplished. Step 3. Sampling. The sampling is state-centric, and particles are randomly sampled from the solution domain of the measurement function. The sampling region should be narrowed when the iteration increasing. Step 4. Crossover and mutation. Crossover operation and mutation operation of GA are considered in the proposed scheme to improve the precision of the solution. By introducing crossover operation and mutation operation, a variety of particles is enriched, which help to avoid the trap into local optimal solutions. Step 5. Find out the optimal solution. Calculate the thickness wall value of each particle according to the objective function. Then find out the optimal thickness wall and its corresponding solution. Step 6. Weight update. Firstly, calculate the thickness wall of the state, then compare it with the thickness wall of each particles. If the thickness wall of the particles is larger than the thickness wall of the state, the weight of the particle is set to 0. Otherwise, the weight of the particle is updated according to the distance between its thickness wall and the thickness wall of the state. Step 7. Resembling. As iteration goes on, difficult particles might be decreased significantly, which lead to the optimization coverage permanently. When the number of effective particles is less than a threshold, the resembling process must be stopped. Step 8. State update. Update state according to particles and their weight. Step 9. When the iteration is over, output the optimal solution of the last iteration, which is the global optimal solution of the object function. We have conducted several simulations to test the performance of the proposed scheme. Table 1 shows the expected return rate and its corresponding covariance of the portfolio, which is composed of 3 securities. Then we optimize this portfolio optimization problem with the proposed scheme and compare it with some relay schemes. Results are presented in Table 2. As we can see, the optimal solution of the proposed scheme is smaller than other schemes. The optimization accuracy of the proposed solution is higher. In this simulation, we had used more input to test the performance of the proposed scheme. Table 3 shows the expected return rate and its corresponding covariance of the portfolio, which is composed of 6 securities. Results are presented in Table 4. As we can see, the optimal solution of the proposed scheme is still smaller than other schemes. In this paper, we propose an optimization scheme for solving portfolio optimization problems. To improve optimization position and avoid the trap into local optimal solution, particle fillet method is considered. Crossover operation and mutation operation of genetic algorithm is introduced to improve the proposition of a solution. Simulation results have demonstrated that the proposed PF-based scheme outperforms the GA, PSO, and SA-based methods. The investment risk optimized by the proposed optimization scheme is smaller than other methods. The proposed optimization scheme provides a more effective and high precision way to optimize the portfolio optimization problem.